These are your 3-1A notes, systems of equations. Systems of equations are two or more equations with the same variables. And when you solve a system of equations, you're finding the values of the variables that are solutions for all the equations in the system. So we're going to really concentrate on a system of two variables with two equations. So we'll solve for x and y, and each equation will have an x and or a y. You can even solve for three different unknowns, x, y, and z. You just have to have three equations, so you'd be solving three at a time. And there's even times where I think in pre-calc they will even do four equations with four variables. Right now we're just going to stick with the two. There's more than one way to solve systems of equations. And so the very first method we're going to talk about is by graphing. It's not my favorite, but I love how it gives you a visual of what's actually going on when you solve a system of equations. So to solve by graphing, when you have an equation, it's a line. Remember, each equation has a line associated with it. It's just the name of the line. So you're going to graph each line. And then the intersection of the two lines is the solution. So where the two lines intersect, if they intersect, is the solution. And we write that solution as an ordered pair. And lastly, my delay is not working here. Ordered pair is a solution for both equations. So when you get that ordered pair, it works for the first equation. When you plug it in, you get a true statement. And when you plug it into the second equation, it gives you a true statement. So it's an excellent way you can quickly check your answers. There's a little bit more terminology here that we give Algebra 2 students rather than Algebra 1. So if you look at these three different scenarios, this is the three different things that can happen when you solve a system of equations. When you graph two lines, the two lines can intersect, which means you have one solution, and it's just the ordered pair x, y. So you write the actual solution. Do not tell me that they're intersecting lines. I can see that. Do not tell me that there's one solution. Actually name the solution. Okay, so you're interpreting what intersecting lines means. This also means that this system is consistent and independent. The consistent part is saying that it has an answer, and the independent part is talking about the two independent lines. For the second scenario, you could actually graph two lines, and it ends up being the same line. So I want you to make a note to yourself that there's actually another whole line underneath the line given here. Make a note that says there's two lines on top of each other. So when you graph and you get the same line twice, that means every ordered pair that worked for the one line also works for the other line. And so every ordered pair is a solution for both. You'll never run out of solutions, so that means your solutions, there are infinitely many. So you can use the infinity sign and just say infinitely many. Again, don't tell me that there's a same line. I need to know the solutions. So you interpret what the same line means. In this system, it's called a consistent and dependent system because consistent means there are solutions, but the lines were dependent upon each other. They weren't two separate independent lines. The third thing that can occur when you graph two equations is that if they don't intersect and they're not the same exact line, that means that they're parallel to each other. And parallel lines never cross, and so they'll never have a common ordered pair. So this is no solution. Again, I don't want you to answer parallel. I want you to answer no solution. I want you to interpret what parallel lines means. Since there's no solution, then we describe the system as inconsistent. The other two systems had solutions, so they were consistent. This one doesn't have any common solutions, so it's inconsistent. So we're just going to kind of incorporate some of that vocabulary along with the solving. So I got three problems for you. The first one, y equals 2x. Pretty simple. Just as a review, when we graph lines, y equals mx plus b is the form that we can get it in to graph the easiest. So if you look, this 2x really has a plus 0 after it. So that's my y-intercept, and my slope is equal to the 2. So 2 over 1 slope means I'm going to go up 2 for every one that I go right, and then my little b is where I'm going to start graphing from. So I'm going to start at 0, 0, because my y-intercept is 0, and then I'm going to count up 2 and go over 1 to the right. Do it again, up 2 over 1 to the right. If I reverse and go down 2, I have to reverse and go to the left, and you notice that they all line up nicely. So you connect and extend that line using a ruler if you need to. And that's our first system. And so remember, when we graph the line, we are saying every single ordered pair, a continuous of ordered pairs, whole numbers, fractions, decimals, forever and ever. If they fall on that line, they are the solutions to y equals 2x. Those are all the numbers that when you plug in x times by 2, it equals y. The second system here, 2x plus 5y equals negative 12. A little bit more work has to be done. So I need to get it into this form. And so the first thing I'm going to do is I'm going to subtract 2x from both sides. Okay, and so we're left with 5y is equal to negative 2x minus 12. I put the negative 2x out in front to put it in slope-intercept form. I need to get the y by itself, so I'm going to divide by 5. Everybody gets divided by 5. And so I end up with y equal to a negative 2/5 x minus 12/5. So going through those parts, it's in y equals mx plus b. My slope here is a negative 2/5 slope, which means I'm going to go down 2 for every 5 I go to the right. And my y-intercept, my little b value, is negative 12/5, but as a decimal, that's negative 2.4. So when I graph, I'm going to use negative 2.4. It's not the nicest problem, but you'll see the points in just a second. So I'm going to start at this negative 2.4 on the y-axis. So negative 2.4 is almost halfway between. And then I'm going to count slope. So I'm going to go down 2. Now I know I go off the page, and it's okay. Down 2 units. So I end up here, and then over 5. 1, 2, 3, 4, 5. And then I got to do the same thing. Go up 2 units. So up 2, 1, 2, and 5 to the left. And I'm kind of in my problem here. But if you see where all these line up, it's right through that wonderful point on the red line. So as long as you're accurate and you use graph paper and you use a ruler, you should hit nicely. So I can see that these are intersecting lines. And not only are they intersecting lines, they intersected here at this point, which is negative 1, negative 2. So that's the ordered pair, negative 1, negative 2. I'm not going to check all of them, but I would like to check this problem with you so you understand what that means. Negative 1, negative 2 is a solution because when I plug it into y equals 2x, and I plug negative 2 in for my y value, and I plug negative 1 in for my x value, you can see that negative 2 equals negative 2 is a true statement. That means it's a solution. When I check it with the other equation, 2x plus 5y equals negative 12, and I plug negative 1 in for x and plug negative 2 in for y, I end up with negative 2 plus negative 10, and that truly is equal to negative 12. So because the two sides balance, that means it's a solution for both. That ordered pair is on the red line. It's also on the blue line. It is the only ordered pair that those two graphs share. So my solution here, if I were to write this, and this is my homework, I would give the ordered pair negative 1, negative 2. Okay, 2 more graphs. The next graph, it's already in slope-intercept form. I recognize that my slope is 3, and my y-intercept is negative 1. So when I graph my green line, I'm going to start at negative 1 on the y-axis. I'm going to count up 3 units, 1 to the right, or down 3 units, 1 to the left. There's my graph. And my blue line also has a slope of 3, and its y-intercept is 4. So I'm going to start at positive 4 on the y-axis. I'm already at the top, so I'm going to go down 3 and 1 to the left. Down 3 and 1 to the left. And you can see if I have the same slope of 3, I'm going to have parallel lines. That's kind of the definition of the slope of parallel lines, is that the slopes are the same. So even though you can recognize that just by looking at the equations, I could see that right here, that they had same slopes. And if you have same slopes, they're going to be the same, either parallel or the same line. You still need to show me your work. So the graph is your work. Your graph is your justification that your answer is no solution here. If you just write down no solution without the graph, I don't know how to verify that. Were you guessing? I don't know how you got that answer. So the graph is your work. It supports your answer. All right, next problem. My red graph is already in slope-intercept form. My slope is -3, and my y-intercept is +1. So I'm going to start at 1 on the y-axis, and then my slope is a down 3, 1 to the right, or up 3, 1 to the left. So here's my red equations graph. My purple equation needs some work, so I have to subtract 9x and get y by itself. So I bring the 9x over to the other side. That leaves me with a 3y equal to -9x plus 3. When I bring the 9x over, I cannot put it with that 3. They're not the same thing. Now to get y by itself, I'm going to divide everything by 3. So y is equal to -3x plus 1. If you look at my purple equation now, it looks just like my red equation. They just disguised it. So that's what they're going to do in the homework. They're not going to give you two of the exact same equations. They're going to make you work for it, but what you can see is that it would be the exact same line. I'm not going to check that you graphed it twice, but now that I recognize that they're the same exact line, I need to interpret that. So my solution here is infinitely many. Infinitely many means I'll never run out of solutions. Every ordered pair that works for one also works for the other. Infinitely many is different than all reals. That point right there on the graph is not a solution for both. So if I said all reals and all combinations, that implies that every number in the coordinate plane works. So a little bit different. Infinitely many means just I don't have one solution, I can't name them all, so I drew you a picture and I'm recognizing that there's an infinite supply of solutions. Every ordered pair on the red line works and is a solution for the purple. All right, so I want you to draw a sketch of an inconsistent system of equations. Okay, open-ended, you got lots of different choices there. And then I need you to solve this system of equations by graphing. So I gave you a few, you had to do a couple steps there to make sure that it works. Solve for y first. Good luck.